My name is Eitel Loria. I'm a professor at the School of Computer Science and Mathematics at Marist College. I'm also the senior data scientist of our learning analytics project. We're going to do the following. Sablado was mentioning. I'm going to start with a presentation, then I'm going to pass it on to my two colleagues, Edward Persuti and Matthew Sokolov. So let me start by giving some context of our work. For those of you who have been coming regularly to LAK, you probably listened to us talk about the Open Academic Analytics Initiative at Marist. It is a project that we launched several years ago. Was initially funded by the Gates Foundation. The purpose of the project was to use machine learning to develop an early alert network framework, that would allow us in the early stages of the semester to be able to detect students that were at academic risk, and then once detected, effect interventions on them. We had a little twist on the project. We followed on the lead of some ongoing research at the time, some work by John Campbell, but our twist in this case was that we made the project fully open source. It was actually the first fully open source project. Marist has been a proponent of open source software for a number of years. And has implemented Sakai, which is one of the large learning management systems in the open source space. We used the Pentaho Business Intelligence Suite, as it was called at the time. In particular, two tools in there, one which is Weka, very well known Java library in machine learning, developed in New Zealand a number of years ago, and used a lot in academia. And together with it, we used integration, ETL tool, also as part of the same suite, which is called Kettle. Although our project was eminently open source, because we have a very long-term collaboration with IBM and very tight relationship, I would say. The first stages of the project, we used IBM SPSS modeler to do rapid prototyping. Then we migrated the whole platform to an open source environment. So this is basically what we did at the time. We framed the problem as a binary classification problem, discriminating between students that were at risk and students that were in good academic standing. And we took, at the time, 4 data sources: student academic data, student demographics, which has been more or less typical in the previous research out there, but we added activity data coming from the learning management system. Sakai in this case, and we were collecting data like number of times in which the students had logged into Sakai, logged sessions, accessed lessons, posted tests, resources, etc. We captured this data in the forms of ratios of counts between the particular students and the average of the class. What we also did at the time was to collect partial contributions to a final grade, which was novel in the sense that, well, when you think in terms of grades, partial contributions to the final grade of the class is mostly the territory of the students and the faculty, but never administrative data. So the ability to capture this data centered by the faculty member into the gradebook that is part of Sakai allowed us to create a metric that we could actually use as part of our predictive modeling framework. The data sources were eminently relational, so we use a relational storage, we use MySQL, and then we kind of follow kind of standard practice in machine learning or data mining. We did all the extraction, transformation, and loading using a combination of Kettle to create, I would say, the workflow, and mostly a collection of SQL statements. And then we did all the predictive modeling in Weka. We created a number of different classifiers. We tested which was better, and so on and so forth. And with that, we ended up with this library of classifiers that we could use from there onwards to score new data. So incoming data from the students was able to be classified using these classifiers, and with this make predictions on the students and submit them for intervention. That was a whole framework. So it's important to consider that, as I was mentioning before, given the nature of the hardware and software that we were using, this was a single node architecture. Let me show you some of the results, which again we've shown in past editions of LAK, but just to refresh the memories of those who've seen this. Using Marist data, which is, we use Marist as a test bed, 3 semesters of data, 2 semesters for training, 1 semester for testing, 25,000 records each. You have to understand Marist is a 4,500 undergraduate institution. We got 87% recall and false positives of around 13%. I'm focusing on those 2 metrics because the data set at Marist was very imbalanced. Marist is a bit of a preppy school. We don't have too many students at academic risks, generally speaking, 3 to 5% in any given semester. So that means that, well, we needed to use those kind of metrics. Recall basically is a metric that will allow us to detect the proportion of students that were really at risk over the total number of students that were at risk. From there onwards, we run this as pilots as a number of institutions, namely 2 community colleges in California, 2 historically Black universities, mostly focusing on first-year courses, 2 semesters in this case. We had a lot of data quality issues in terms of the ability of our partners to be able to deliver good quality data, but still, I would say, praising the robustness of many of these predictive modeling tools, we got pretty good results. On the average, 71% recall, 22% false positives. But in those institutions where we really got good data and we were able to use the same kind of predictors, we pretty much paired the results that we got at Marist, 81% recall, 16% false positive rates. The project was well received. It was kind of seminal work, in particular when it comes to some of the predictors that we use and the fact that this was an open source platform. So we received a number of accolades. I'm going to blow my horn a little bit here. And we got a number of awards and stuff, so we're very happy, I guess. Well, Marist became our platform that received the name of Learning Analytics Processor from there onwards, for lack of a better name, I guess, or LAP, as we call it nowadays, became de facto reference architecture for learning analytics in the open source space. Now, we considered at the time what would be naturally the evolution of this platform. And the evolution of this platform, of course, had to do with improving some of these numbers. And this is not working. Well, trying to improve recall, trying to improve false positive rates. In reality, this is not so much about improving the algorithms, or could be up to a certain extent, but it's perhaps much more about identify better features or expanding the volume of data, and in particular the variety of data. So 2 things to consider here was the whole stage of preprocessing was laborious, especially when capturing all this activity data. But then it had to do with the fact that we were creating these predictors and we were limiting ourselves to these 4 data sources that I was mentioning before. So we thought what we could perhaps do is expand or broaden the variety of predictors. So our next stage was to consider not only the current data that we're using, but also future data. It could be library data or student engagement or social network data, or within the parameters of legality, if we're able to get access data to the dorms. I imagine that if a student arrives every day at 4 a.m., well, probably is going to have a problem. So if we were able to gather that kind of data, it could be actually useful. So the point with that is that that's a massive amount of data of different qualities, no longer relational data necessarily. We may be talking about semi-structured or unstructured data. And for this, we needed to be able to scale. So 2 solutions to this: either we scale up and we get a larger computer, IBM would be very happy, I guess, or we scale out. And scaling out means perhaps distributing this in a dynamic manner and putting more workers to work, depending on the workload that we're receiving. And for that, what has proven to be extremely effective, we see with every search engine out there today, is big data oriented platform, which is naturally cluster computing. So that was our direction. So we implemented a cluster computing architecture as opposed to a single node architecture that we used to have. And again, the natural environment in an open source platform was going to be Hadoop, which is what we implemented. So in the layer here, we implemented Hadoop that takes care of all the distributed file systems, plus the, let's say, distribution of resources across nodes with its own resource manager, and some processes running what was the original, let's say, platform with which Hadoop was delivered, which is MapReduce. On top of this, we have the ecosystem of different tools that we have used. In particular, I'm going to make reference to 3 because they are kind of aligned with the previous slide that I presented. So for ETL, we use Hive, which is a kind of a SQL-based environment that translates into MapReduce. Then we use Spark, which has been the dominant force in the data mining community tied to big data and cluster computing. We do a little bit of pre-processing of data in there also. We use Python as the API. We decided to not go in the direction of scale and mostly just to flatten the learning curve, I would say. And then, again, we followed suit. We trained the models. We trained a certain number of classifiers, and with this, we scored the data. With this, well, we were able to score new data, make the predictions, perform interventions. I'm going to pass the baton to Ed that is going to proceed with the presentation.
Thank you. My name is Ed Pursuti. I'm the manager of data science and analytics at Maris. I need my glasses. So, not knowing how to work the baton. Part of the problem of moving to the big data environment is you've already established a code base, or we had already established a code base, which was written in SQL, MySQL database coming inbound, and now you're switching to the big data platform. As Hitel just mentioned, we selected Hive. One of the reasons why we're using Hive is because there was a domain knowledge already. You have people that know how to write SQL, you've used SQL, so why not use that tool? Or you can go down the path and try to teach everybody MapReduce, which was definitely not the direction that we wanted to go. That was a long path to get to where we needed to go. The other issue that was in the first platform was the large number of queries that were already written, and the fact that we could take advantage of some of that work that had already been done. So basically, coming out of the MySQL database was a series of 5 tables that fed the ETL. So that's what we're looking at right here is we scooped out of MySQL basically data that had already been pre-prepared, fed that into Hadoop, put it in the flat structure, used Hive as the ETL, which then reduces it to your unit of analysis, and then feed that into Matt's portion of the presentation, which is coming up just one second. So the other product we used was Oozie, and Oozie to control the flow. We had a relatively small set of nodes. We only had a 5-node network, so it wasn't a huge Hadoop cluster. And what we discovered was early on that we had undersized it. So when you start moving to these platforms, it's important to look at what your processing power is going to be, how big that ETL process is actually going to get, and what it looks like when it distributes across. The reason why there's 3 nodes at this level is because 4 nodes broke it. It just actually stopped the cluster from operating. So that was a hard lesson to learn early on. The other lesson we learned along the way was that we didn't really need to break this. This could have been linear, because you're talking about generating a unit of analysis on a daily basis. So if that runs in a half hour or an hour or anywhere underneath 24 hours, you're probably going to be okay, because your data's not changing that frequently. Our process ran in about 20 minutes, so it was perfectly reasonable, but we did have to break it up. So what did we learn? Well, HQL is not SQL. You are not dealing with a relational database. You are dealing with a flat file structure. So early on in the process, we had written views, and we thought we'd take advantage of that, and that just didn't work out. We wound up creating a whole series of intermittent tables, which actually sped the whole thing up. So when you're migrating to this platform, bear in mind, the engine on the other side of it is eventually effectively just a series of CSVs. So you have to keep that in mind as you're moving your data there. The other thing we learned is we would have been better off starting out with CSVs, dropping those down as external tables, leaving them in structure, and then you can deal with any number of elements across that, so that you don't have to worry about embedding that data in the Hive engine. The metadata is all you need to worry about, and then you can use external stores and just move files in whole or in part. If you need to append to files, there's really no such thing as an insert in Hive. There's no such thing as really a delete. You're really dealing with large sets of data that just needs to be dropped down and kept in place. So with that, here's some of the volumes we achieved from our friends at North Carolina State University. And we wound up being very successful. But one of the things that we ran into was not completely understanding what the artifacts of the Hadoop cluster were going to be on the Linux file systems. So that's important to understand as you move into that. What resources are going to be occupied? How are those resources going to be distributed? And as they're distributed, what Linux space does it take up? What's your memory utilization? What's your temp space utilization? All that stuff is going to matter as you build these clusters out. So Matt's going to talk about the modeling aspect of things.
Hi everyone, Matt. I'm a graduate student and I work in the data science department at Marist. So here's some of the topics we're going to cover in the upcoming slides. As Untitled had said, we used the Spark environment and we used the machine learning libraries, both ML and MLlib. We'll talk about why we had to use both of them in a couple slides. Some of the algorithms we used was logistic regression, decision trees, and naive Bayes. Logistic regression actually ended up having the best performance, so that's what we are currently using in production. There's 2 main architectures. There's a training and testing flow. The training flow actually looks at all of the historical data and then creates a model that we can use for figuring out which students will be at risk, and we actually apply that model in the prediction flow. So the process starts with loading the result of the ETL, which Ed had explained, and at that point in time, the data is missing a lot of values. For whatever reason, it didn't get entered. and the data is also skewed, so there's a lot of kids who pass, especially at Marist. So what we have to do is first fill in the missing values, and we simply assign the mode to categorical variables and the mean to continuous variables. And that essentially tells the model ignore those values. And then we apply sampling for the training flow. So what we want is an equal distribution of students who pass and fail, so that the model doesn't favor any one particular class. To illustrate this, if the model predicted that everyone was going to pass and didn't consider the data at all, it would be 96% accurate, and that doesn't do anything for us. So once the data is sampled and all the holes are filled in, we have to use the machine learning libraries provided by Spark, and we'll talk about that a little more on the next slide. And then if we're actually making predictions, we have to load the model, which we have saved in different projects as either a distributed object across HDFS, or we save the weights so that we can actually turn off the cluster and just save it on a single machine. And then once we make a prediction, we save those values, and they can be used by whoever wants to intervene. So there's when you consider the performance of the model, there's more to it than just the accuracy. Again, going back to the Marist example, 96% accurate doesn't mean that it's necessarily performing well. So you also want to consider other things such as recall and false positive rate. Okay, so going back to the ML pipeline, what we did to make sense of categorical variables was we use something called string indexer, and it's an alternative to one-hot encoding if you're familiar with that. And then you would use ML to apply the machine learning model. And Spark ML is it's a really useful library because it greatly reduces the amount of code necessary as compared to MLlib. So we actually ended up using Spark ML 1 month after it was released, and this is something that may be valuable. It didn't have a saving feature, so we would train the model and we couldn't actually use it. So that's why we had to reincorporate the previous generation of Spark MLlib. So by combining both libraries, we were able to have a much smaller piece of code so that it was easier to debug and just look better. And then we would use MLlib for actually performing the predictions or learning the weights, and then we would save that model. So I'm going to hand off to Untitled to finish off the presentation.
Following on what Matt was saying is, one takeaway is that these are great platforms, but they're profoundly mature, so they're in permanent evolution, and we are always in the learning curve in a certain way. So let me get my glasses. Where we are. So this is Promising Outcomes 2. This is what we run. Basically, what we were trying to do is make sure that we would able to replicate what we had done at Marist. Of course, at Marist, we got the same results. Similar algorithms in different implementations, but we got 87% and 14% of false positive rate. We have been working with North Carolina State for a while, so we're running there 3 semesters, 160,000 records each. We got recalls of 77% and 18% false positive rates. When we run on our purely online data, which is 85% records in this case, we got much better recall. There's an explanation for that. When you think in terms of online courses, it means that the types of tools that are being used in a course are much more homogeneous. If they're more homogeneous, there are less holes in the data. That means you have more predictors because there are more of those variables that describe activity that may actually be used. We still have to work on the false positive rates. That means that with those levels, and even at Marist, it's not something that we can transfer directly to the student, because we don't want to say, student, you have to get your act together, and the student has an A. So, but again, it's this part of this learning process of moving in the direction of creating applications that allow us to make early detection. At this point, this is being delivered to a faculty member, and of course, it's a good aid to the faculty member because a student may very easily fall through the cracks. With this, we are able to really detect students that have trouble. So NCSU is currently implementing the Maris lab framework. Maris Lab has also been chosen as a key component of the UK's national analytics infrastructure, which is provided by GIST. GIST is a technology institution that provides technology to more than 100 campuses in the UK. At this point, we're working with a number of universities. I think that Brits are trying to make fun of us because they provide us with all these names, and I'm completely unavailable or unable to pronounce. I come from Argentina. How the heck I'm going to pronounce this, for example? But what? That's a different story. So in any case, this is the end of the presentation. I would like to open the floor for questions. Thank you very much.
Okay, so we have time for a few questions.
Question about the internal infrastructure that you set up. It's quite complex. How many people, just curious about, this is like analytics, big scale implementation. How many people in total, developers, network admins, you guys, managers, how many people is necessary to pull this off?
I'm going to record you so that then we can have our salaries raised. Because the total number of people, including grad students, we have a big asset here. What?
Five.
Whoa.
Yeah.
So network, Hadoop setting up all that.
Maris, I have to say something about Maris. Maris has a technology equivalent to a Research One university, so you ask, they deliver. That's the reality of it. So we don't have to worry as much in terms of getting, I would say, the hardware or the virtualization of the hardware. A lot of what was done here was done in machines that were virtual machines. But all the setup, all the configuration, all the code, everything was done by 5 people, and I would say that probably 2 that really have worked intensively in the code. You want to hire someone, hire this guy. Really. So yeah, but it explains that you can work with, since the moment we started, back in 2011, 2012, I did a good part of initial coding the single node architecture. Few of my artificial intelligence students, 2 at the time, worked with me. Then I had another 2 students, 2 had gone. We were always a group of 2 or 3. When we moved to a platform that was distributed, we had to add some additional people that came along, Matt came along. And in reality, Maris now has a data science and analytics division within the IT department that shines.
What I should have added in my presentation is in the UK, we're actually using Amazon's Elastic MapReduce solutions. So the way that pipeline looks, if you look at the and all the pieces, parts that come with it, is you spin that cluster up, it runs to completion, it stores the data, and then that cluster shuts down. And that's all just managed by Amazon. So you don't need that IT infrastructure.
It is managed by Amazon, but the whole engineering of spinning the cluster, producing the results, and closing the cluster was also done by us. So I think it's relevant to describe that.
Okay, we have some
Yeah.
questions.
Do you have any theories on why logistic regression seem to be a better predictor than brute force?
Logistic regression is a good workhorse. It has always been a good workhorse. So I would say that it has to do with this idea of high bias, low variance, generally speaking. With models that have highly imbalanced data, something if you go in the direction of perhaps trees, for example, that are very expressive, you could have a situation where varying the data set a little bit produces perhaps different results. So I would say support vector machines, especially some of the linear kernels that resemble a logistic regression in some ways, in terms of at least performance, are the ones that work better. But the reality is that we're testing random forests, for example, and a random forest has the ability of kind of even out variance, because basically what you're doing is kind of bagging and boosting lots of different moles. So results are kind of similar. What we originally did was mostly focused on logistic regression because we had similar results. And between results that are SVMs and logistic regression, SVMs are not so explainable. Logistic regression is easy. You just do the exponential of the coefficient, and at least you can explain the log odds. You cannot do that with SVMs. So.
Question here?
Yeah, thank you. Very interesting talk. Okay, so you're using this for predictive analytics. What else can you use the data that you've got for? So what if there's faculty members? I'm thinking from the sort of more learning side. You've got faculty members that want to know something, and they come to you, and you can do something for them instead of doing the machine learning algorithms.
You mean getting input of the faculty members and using that input in the system?
No, more querying and getting information out because you.
Well, of course, this is oriented towards the faculty member. What we're doing at this point is creating dashboards or going in the direction of producing visualization of the results that we actually get. Because
They can come to you and say, we need to know this, can you help us?
not even come to us, in the sense the idea is to putting this up there in their reserve section of the LMS so that they can have data. A couple of things that we did, and we presented this last year. We had a bunch of radar charts that were able to detect along certain dimensions. For example, the dimensions tied to the demographics. How was that student with regards to the rest of the class? Dimensions regarding to activity. And so we could actually plot that and see where it actually spiked. So that is valuable information. But we are trying to consider other alternatives. Visualization is a hot area of research in which we want to improve, really.
We actually started building some visualizations, but we just don't have the manpower to create interactive visualizations for every professor yet. But that is definitely an avenue that could be explored.
Okay, let's thank again the speakers for the presentation.